Alright, so good afternoon. So let's get started. And this is where we stop in the last lecture. So we talk about the MOSFET technology trend, and here we list some of the innovations that the industry introduced to make the scaling going on. For example, we have the gate stack material changed to the high-K metal gate, and this is to improve the capacitance, gate capacitance. So the channel material is also become different than pure silicon. So we apply stress to the silicon to increase the mobility, and also we introduce germanium into the silicon to make the mobility higher. And then the gate structure, we change from the bulk to the multi-gate or the FinFET next structure, which we are going to discuss in more details when we talk about the SRAM design. In the last part of the SRAM design, we're going to discuss, in particular, the FinFET-based SRAM design. And here in the end of this slide, we have this table from the ITRS 2011. So today we're going to continue our discussions on the ITRS table like this. So basically, this is a roadmap for the industry to make the scaling from generation to another generation. And this is a prediction was made at 2011. So you can see that technology node 45 and 32, and then 22, 16, 11, or 8. Nowadays we call it 7. So this is a prediction, but actually the prediction may not match the reality. Here you can see that the 11 nanometer technology node volume production actually delayed to like 17. And the volume production for the 7 nanometer or here the 8 nanometer delayed to like earlier this year. So this is the slow down of the scaling in the recent years, and that was not in this prediction back in 2011. So let's look at the scaling, and we're going to introduce this ITRS table. So ITRS is short for the International Technology Roadmap for Semiconductors. So basically, it's a roadmap that the industry come together and then make the predictions for the technology scaling. And the ITRS actually was a consortium of different members from different countries. And here are the ITRS sponsors. And you can see that from different countries or regions, like Europe, Japan, Korean, and this SIA, Semiconductor Industry Association, is actually US, and this last one is Taiwan. So this is like an industry consortium to basically discuss the roadmap for the next generation semiconductors. And the outcome of the consortium is to produce a yearly report for the technology roadmap. And this was one table from the 2013 yearly report. And here you can see that this is technology trends, targets. That means those are predictions back in 2013. And here in this table, you can see that this is the technology load, like 16, 14. And industry thinks that this technology node should be introduced in this year, but actually it was introduced in roughly like 14, and then next generation like 10, 7, 5. But as I said, those are delayed, as you can see here. So this is a technology node, and we are going to discuss what is this technology node later in more details in today's lecture. So, but at this table, this technology node is more like a symbol for the generation. Let's say generation 1, 2, 3. So it does not mean anything. As we discuss later, you will see that. But in this table, it really defines some of the dimensions for the technology. And for example, here you can see that in this line, we have the metal 1/2 pitch. So this is the first metal, and the pitch is the distance from one metal to another metal line, and half of that pitch is defined as a feature size in this case. And in this 14 or 16 nanometer technology node is like 40 nanometer in this case. And also we have some parameters with the FinFET structure, like what is the fin half pitch, fin width. We are going to discuss those dimensions more details when we talk about the FinFET. Question?
Maybe we can turn off the lights in the front right there.
So turn off the light. Oh, that's good. So here is for the FinFET, and then also for the memory technology like flash, it defines what is the half pitch for the two-dimensional flash, and what is the layer number for the 3D NAND flash. So as you can see here, those are the predictions for the each technology node, and then you can see some of them are actually delayed, but some of them are actually introduced earlier. For example, for the 3D NAND flash today, as of today, I think Samsung just announced the product for 128 layers. And most of the industry will have the 96 layers this year. So actually the 3D NAND flash progress outpace the prediction in the recent years. But the logic transistors slows down in the past few years. So that's a general trend for the industry. So any questions for this table?
So basically, when they talk about a half pitch, what do they mean by?
We will discuss that. Yeah. So that is an overview technology trend, and if you go into the report, it will have the more details in this kind of table. And for example, here in this 14-16 nanometer for the logic process, it will define some of the physical dimensions. For example, the printed gate length is like 28 nanometer. So you see that here, the printed gate length is different than the technology node number. 14 nanometer, 16 nanometer doesn't mean that your physical gate length or printed gate length is 14 or 16 nanometer. It's just a symbol, as I said. So the real printed gate length is roughly 28 nanometer, and the physical gate length is about 20 nanometer. So the physical gate length is smaller than the printed gate length. Printed gate length is the length that you define by the layout. And then when the device is manufactured, then the actual physical gate length may be shorter than your layout, because the source and drain will have diffusion into the channel. So then the physical gate length may be a bit smaller than the printed gate length. So those are the parameters, like also like a power supply VDD. So of course, those are the predictions for the 10 nanometer, 7 nanometer, and 5 nanometer at these days, because the semiconductor consolidation, and there are only a few manufacturers for the, let's say, advanced technology node like 10 nanometer, 7 nanometer. So this kind of table becomes meaningless, because the original idea is that we set a target for the industry to develop the technology following this trend, and we can have some agreement on the technology definition. And nowadays, since this is dominated only by 2 or 3 vendors, then this table becomes meaningless, and then those 2 or 3, dominant manufacturer can define their own specs. So then this table becomes useless. That's why in 2015, I think that's the last ITRS meeting, and after that, I don't think there are updates after 2015. So this is the history for this ITRS. And let's go back to your question, how do we define the pitch? So this is by definition in this ITRS report, and it's still used in the industry. So for the memory, like flash or the DRAM, the definition of the half pitch is very clear. So for the flash, because you have this multiple gates in the flash, as we discussed later, it is a string of the transistors in series. This is like land. So then you have multiple gates. And the gate, historically is a poly gate, polysilicon for the gate. But of course, these days we changed to high-k metal gate, so it's metal gate. But doesn't matter, let's still call it poly. So from gate to gate, you have this pitch. And we define the facial size, F, as half of the pitch. And you will notice that here from the gate to gate, there's no contact in between. So here, this region is the source to the right, but also is the drain to the left. So then here there's no contact in between. So this is called stacked transistors or uncontacted poly. So this is defined as a pitch of the flash, and half of that is defined as F for the flash. And today, still for the two-dimensional flash, the technology load for flash is defined as F here, half pitch.
So that includes the minimum resolution for the metal bits.
That's a minimum resolution for your lithography. Yes.
Oh.
Yeah. So this is for the flash, and for the DRAM. So the pitch is defined as half. Oh, sorry. The pitch is defined as the metal 1. So this is the metal 1, and you have contact for the bit line, for example, bit line to bit line. Then you have the pitch for the metal 1. And then F is defined as half of this pitch. This is also the technology load for the DRAM generations. And I would say for the memory technology like flash or DRAM, the technology load really is associated with the physical dimensions, the pitch in the poly gates or the metal 1 wires.
There's obviously a spacing dimension, and then there's the dimension of the actual gate. They don't. How does half pitch correspond to each individual dimension? The gates are a lot smaller than the spacing in between.
No, here for the NAND flash and the DRAM, this definition is very clear. So here, the pitch is defined as this, from this side of this poly gates to the this side of the poly gates. This is by definition.
Okay.
Yeah, and DRAM is defined by the metal 1 pitch. Let's say your bit line to bit line distance. Of course, here your wire may not be exactly half of the pitch, but still we think the F is half of the pitch because that's the average, the distance between those two.
Can you explain more what's metal 1?
First, the layer of metal.
Oh, okay.
So, any other question? So, here the memory technology. This F really means something in the physical layout. It really relates to the pitch. So this is true for the memory, okay? But the situation will change for the logic. For the logic, it's more complicated. So let's look at those examples first. So this is some layout of the transistor for the logic process. And the first layout, this is kind of isolated transistor because those are individual transistors. And the layout will have some spacing between the individual transistors as isolation area. For example, you have the STI, the channel trench isolation. So this is isolated transistor, and if you look at isolated transistor, the typical cell area will be like even 16 to 20 F square. And we'll discuss what is F later. But here for the simplicity, we think F is this technology load. The symbol, like 14 nanometer, 20 nanometer, or 7 nanometer. And for the contact pitch transistor, the bottom layout is a typical contact pitch transistor. That means here the transistor, those two transistors going to share the contact in between. So for example, this contact can be the drain of the first transistor, can be the source for the second transistor. So they share this contact. If you do that, then of course you save the spacing, then the cell area, let's say for each transistor, equivalently you may only need 8 to 12 f squared for this layout. But of course, if you size up the transistor W over L larger than 1, and if you include the routing and wiring, the actual transistor size can be even larger, maybe like 24 to 64 f squared. So why are we interested in this kind of layout? Because if you look at the real circuit, let's look at a very simple one. You must be familiar with this. Let's say 2-input NAND logic. So this is a circuit schematic, 2 NMOS in series for the pull down, and then 2 PMOS in parallel for the pull up. So this is a 2-input NAND gate. And if you draw that in the layout, a typical layout, something like this. And here this bottom part is NMOS, bottom part is a PMOS. And you will see that these yellow lamps are the gates, right? And for the bottom NMOS, actually here are the so-called stacked gates. This is similar as a NAND flash. You have seen this before. NAND, of course, you have a string of that. You have many transistors in series. But here, for the 2-input NAND gate, logic gate, then you have 2 lamps there because 2 inputs. And this is a stacked transistor because in between those 2 gates, you don't have contact. Why don't you need contact here? Any idea? You don't need contact here. Why is that? Because you look at the circuit schematic here, this node is actually here. You don't need contact to that node because that node is isolated to the outside. So you can save the contact because every time when you insert a contact here, you will consume some space. According to the design rule, you need some spacing between the contact to the gate, contact to contact, contact to the edge. So you need to spend area on that. And then for this NAND logic gate, the pull down NMOS, you can save for that. But when you look at the pull up PMOS, this part, those 2 PMOS are in parallel. Okay. So here, for example, if you read this layout, then those 2 gates, so basically this is input to A and B. So those are the 2 gates here. Right. And then here are 2 PMOS transistors. They are in parallel. Because then this node is, let's say, PMOS here, PMOS source, and PMOS drain. So then this is the source is VDD. And then 2 of them will connect to the same drain contact here, which is the output, which is here, out. So those 2 transistors are in series, in parallel. To make those 2 transistors in parallel, then you must insert the contact in between like this, and they are going to share this contact. So then, if you look at the whole PMOS region, these are the so-called contact gate transistor. So this is contact gate transistors. 2 kinds of layouts for the NMOS and PMOS region. And here the design rule says that below 65 nanometer, if you look at the overall layout of your logic circuitry, there are more and more this kind of contact pitch transistors like this. You have most of the design like this. So any questions? Okay, so then let's look at the ITRS table. This is a history of the scaling from the ITRS. And this is for logic process. Okay, this is for logic. And here we have the year back in 1995. And then the first one is the metal one half pitch. And the second, this kind of green ones are the printed gate length. And then the last one is the physical gate length. So you see this is a scaling trend. And here, let's say at 2000. So historically, we call this printed gate length as a technology node, tech node. And historically, we call this is the F, because this is what you define in the layout, the minimum feature. This is called the F, and this is the technology node. This is true till 65 nanometer. So let's say at 2000. So here this node actually is 130 nanometer node. And every 2 years we scale, right? So this is 90 nanometer. And then this one is 65 nanometer, let's say around 2005. It's roughly 65 nanometer here. So above 65 nanometer, if you go back, like 65, 90, 130, 180, 250, and 350. So in those technology nodes, the F really means this printed gate length. Okay. But after 65 nanometer, you see the trend slows down. If you draw the line here, so after 65 nanometer, then this slows down, right? You see a discrepancy between the projected printed gate length and the actual gate length. So you see the difference here. But the technology node still keep this kind of scaling. That's why it becomes meaningless, because it becomes more like a symbol, right? Because it does not relate to the actual printed gate length anymore. So that's why if you keep that to this trend to today, it's roughly 7 nanometer, right? So if you do it, I didn't draw it very well. But roughly here, in that 7 nanometer today. But the actual printed gate length or the physical gate length is still like maybe 15, 16 nanometer, even 20 nanometer for today's so-called 7 nanometer technology node. Those two parameters totally decouple.
I know you said it's completely decoupled, but is there some logic behind it that, well, if you have a short channel effect, that doubles in creating like an effective 7 nanometer mode?
So no. So this 7 nanometer becomes a symbol or for the industry. Does not really mean anything physical. So the physical or the printed gate length is still like 20 nanometer for the 7 nanometer load. And this is exactly due to the short channel effect you mentioned, right? So it's very difficult to control the leakage current if your physical gate length is really small. Because you know the electron, the wavelength for the electron is 13 nanometer. Because the electron, you know, due to the so-called wave and particle duality, due to the quantum mechanics, you can think the electron is a particle or at the same time is a wave. If it's a wave, then the wavelength is 13 nanometer. That means if your source and drain are 13 nanometer apart, then you have some probability to find the electrons in the drain, even without turning on the gate, right? Due to the tunneling. So this is why the physical gate length cannot be really small. So then this technology node becomes a symbol. But still, I think in your homework, you are going to use the technology node as F. Okay. When we normalize everything to be F squared, then you are going to still use the technology node as F. So at 7 nanometer, then F squared will be 7 nanometer squared.
Excuse me, Professor. So did you say it's both the printed gate length and physical gate length both slowed down, or only one?
Both slowed down, yes. And because initially the physical gate length, here you can see here, scales very aggressively, but later it also slows down because the physical gate length actually determines the short channel effect.
So how can they define whether it's 7 nanometer or 5 nanometer?
So it becomes meaningless. It becomes a symbol of, let's say, a marketing in stuff, right? I mean, you think the 7 nanometer becomes 3 nanometer, and the physical gate length actually doesn't scale.
Then why Intel claim they have reached the same gate length as TSMC is?
So that's also an interesting point. I mean, different companies, when they talk about the technology load, it seems to me Intel's 10 nanometer is equivalent to TSMC's 7 nanometer in terms of density. We will talk about that in a minute, what really is scaling. So that relates to this question. What is really scaling if the physical gate length does not scale, but still the scaling is going on? At least it's true for today. So what determines the logic transistor's density is not the physical gate length. Actually, it's this gate pitch and the metal pitch. So that's why we have that contact gate pitch transistor like this. What we care about, if you look at the layout, we don't care about this yellow line, how wide it is. That is the printed gate length. We don't care about that. What we care about is the density or the area for the whole circuitry here. So what we care about is this and this. So if we draw here, this is a gate pitch for the contact gate. So that means you have contact here and contact here and contact here. So what is important is the, let's say, from here to here.